Okay, welcome everybody. It's my pleasure to introduce our colloquium speakers today, Professor Ricardo Comin. He is a friend to some of us, having actually gotten his PhD in Canada and postdoc here. So his background, let me just say, he did his master's earlier education at the Universitat de Trieste, and then he went to UBC for his PhD. And after that, he came here and did a very interesting postdoctoral work on photovoltaics. And soon after that, he went to MIT, where he's been faculty since. And very impressively, he's been really prolific since going there, especially in recent years and throughout the pandemic. If you just look at his publication, there's a variety of things that he's done with his expertise, which is using various established methods of light interacting with solids. He's able to probe many interesting quantum phenomena. You can call this kind of like, quantum materials studied with light. What I find fascinating, having worked with him a little bit, is he literally took some of these established techniques and found new ways of extracting novel information from them. One work that's notable, before I give you some of his honors, is he's able to, recently, there was a work where he was able to measure using this technique called angle resolved photo emission, if I got that correct, to literally measure the quantum geometric tensor in solids. So loosely speaking, you infer at the shape of an photoelectron that way, which to me is really remarkable for a technique that's been known, but is showing you sort of new light. And let me just give you some more background. He has already his, relatively short career so far, won many awards. Three are very interesting to mention. The John Polanyi Prize in 2015, the NSF, National Science Foundation Career Award in 2018, and most recently, the Friedrich Bessel Award from the von Humboldt Foundation in Germany. Now, today he's going to tell us about a new class of materials, altermagnets, which you can argue is a new type of quantum material. And he's also an expert in superconductivity, another very well-known class of quantum material. So there's a variety of things he does. So without further ado, I'm going to just welcome Professor Comin for this colloquium. Thank you. Sorry, I forgot to mention one thing that we got over. Today we're over lunch. We found something interesting that he still remembers from his Toronto days, which he saw in MIT, in Boston, in Cambridge, that you have to be an extreme biker to get from home to work, if you know what I mean, dodging all the cars. Anyway, that's sort of one fun thing he remembers from here. Sorry.
It's working? Okay, great. Thanks, John, for the invitation. Thank you all for being here. It's great to be back in Canada, in Toronto, especially these days with all the madness you hear from south of the border. But I won't dwell on that. Yeah, I was here for 2 years for my postdoc. I was in the Galbraith building. I was sort of like an undercover physicist in a group full of engineers and chemists, which was actually a lot of fun. I was doing this, photovoltaics and optoelectronics. I was taking a little bit of a sabbatical from quantum materials to explore something else. And it was challenging because it was very different from, anything I learned previously, but it was very rewarding, actually. I learned a lot from a lot of people, and I still have many connections. Eventually, I decided quantum materials were more interesting, so I decided to pitch that for my research program at MIT. Interestingly enough, as I was telling John, when I came into this room, I had a flashback because I remember in 2015, I think, it was just a few weeks after I did my interview at MIT, and John had invited Jagadish Mudira, who was a big expert in magnetism, and also based at MIT. And he gave a colloquium in this very same room. And I remember coming for the specific purpose of actually meeting him after the colloquium and asking him, how things are at MIT, is it really cutthroat as people say, and is there a lot of competition? And he was like one of the nicest person I talked to, and I was like, wow, if everyone is like him at MIT, I should really go. So I guess that was a good presage. Anyway, so I'm here today to tell you a story about this new class of magnets. I'm kind of regretting a little bit using this title because there's a lot of technical terms here, but I'll introduce all of them during the course of my talk. I'll explain what a non-conventional magnet is, what an altermagnet is. Those two are kind of closely related. And then what I mean by P-wave, which is, of course, a name that is associated to certain orbital physics and also superconductor physics. See. Oop. Okay, I'll use the computer for the. Especially nothing is happening. Oh. Okay, great. Thank you. So this is the menu du jour. Just using French since we're in Canada. So I'll start with about altermagnets, what they are and why do we care, or why are people excited about them. Then I'll talk about this class of non-collinear magnets, which broadly go under the name of spin-chiral magnets, as a platform for this very peculiar kind of altermagnetism that has this special P-wave character to it. And then I'll talk a little bit about some experiments we did on how you can control this using electric fields, and why that's potentially interesting. And I'll talk a bit more about, in particular, this material, nickel iodide, which is very simple material, but very rich physics. So before I start my talk, and I don't want to have this as the last slide because I want to make sure I give credit where it's due. I'm just a marketing guy, as you know. The people who actually do the work are the students and the postdoc. The one I want to give a particular shout out to is Chan Song, who spent most of his PhD basically working on this specific material I will tell you about today. And it was really the driving force behind this project. He's like, he's done formidable work, and he's now at Berkeley with Ramesh, and he's going to start his faculty position next year back in China. Then many other people were involved, in particular Jaruo, who did some nice work on devices. I will just flash out one slide at the end to show a possible application of this P-wave magnetism. And then many collaborators at MIT and various research facilities, but also in particular, I want to give a big shout out to our theory collaborators, group of Silvia Picozzi in Italy. She's an expert of ferroelectrics and multiferroics that turned out to be critical for understanding this material. Sang-Wook Chong, who's, of course, is primarily an experimentalist, but turns out that his insights about symmetry were very important for this work. And then Rafael Fernandez and Daniel and Jorn, who did all the symmetry analysis that I'll present later. So why do we care about magnets? And then I'll get to altermagnets later. So in this world, we kind of have a data problem, and it's getting worse, and it's getting exponentially worse. So this is a chart that's up to 2025, and I had this mid-year. So this is not even. I think this grew even taller by the end of the year. This is the data generated in what is a frightening unit, which is zettabytes, which I had to actually look up. I wasn't even sure what that prefix, that Greek prefix, stands for. But let's just say it's an enormous amount of data, and it's trending exponentially. Okay, and with the advent of AI, of course, we know that this is going to become a bigger and bigger challenge. Now, interestingly enough, most of the world's data are still stored on magnetic drives. So this is a similar plot now, with going back to 2010. This is a histogram plot that shows you basically what percentage of various storage technologies the data used to be stored in. And if you go back to 2010, actually, a lot of it was in sort of optical and tape. And it was hard drives, of course, were already big. There was the majority of the market back then. And then hard drives kept growing, and they're still like very reliable sort of platforms to store magnetic data, but they're kind of slow. And so over the years, new platforms have been developed, like SSD, which is sort of like the flash memory drives that you have now in your phones and your computers, and because they're much faster, right? But as you can tell from just looking at this plot, basically 50% of the data are still on hard drives across the world, and like a good maybe 10-15% is on tape, and it's been growing, which is, I think, remarkable, right? That's the sort of like the really robust, ultimate line of defense against loss of data, right? A lot of these data are backed up onto these magnetic tapes. So that's why magnets are important. And of course, magnets are used in a lot of other technologies, but I want to specifically flesh out applications in storage, because that's what altermagnets have been proposed as a potential new technology. Now, the good news is that there's plenty of magnetic materials. So there's continuous development in this space of materials. And this is kind of fueled by the fact that actually a pretty significant percentage of all known material is magnetic. It's actually almost 50%, which when I actually saw the data, this is from the materials project, I was actually very surprised. I thought it was more like 10, 15%, but it turns out it's actually much more prominent than I imagined. All right, so if we go back to the basics of magnets, let me just move this cursor out of the way. So the simplest kind of magnet we know, and one that has been known for millennia, literally, like the name itself, magnet, comes from the Greek word magnesia, which is related to, it's the place where the very first magnetic materials, magnetic minerals were discovered, is a ferromagnet. Okay, so a ferromagnet is just a material where the predominant interaction between local magnetic moments is of the ferromagnetic type, which means the local magnetic moments or the spins, if you take a quantum description, they want to be aligned, and so you have a net total magnetization in your material. Okay, and here I'm going to adopt a simple kind of model where basically the spins can either be up or down. So you can think of this as essentially it's like an Ising model, or is a model that neglects spin fluctuations. Right. So, and the description of ferromagnetism has been around for a long time. Pierre Curie was one of the founders of the field and really the early developers of the theory of magnetism. And what we know in terms of symmetries, and this is important because our symmetries are going to play a very important role in this talk that I'm going to present, and in general in this field of altermagnets. When we think of a ferromagnet in terms of symmetry, there is a very evident symmetry that's broken, which is time reversal, right? When you apply time reversal symmetry, you're changing the direction of the magnetic moments. That's because if you think of magnetic moments as sort of axial vectors, so kind of like or circulating currents, if you like, when you change the arrow of time, those circulating currents go in the other direction, and the magnetic moment changes sign. And when you change sign to the magnetic moment, now you're turning your ferromagnet, which was wanting to have spins pointing up, now you change it to having spins pointing down, and these two are clearly different. So that symmetry is broken. So this is the real space picture. Now, if you look at the reciprocal space picture, which is really the space where the electrons live, and if you assume that your material is a metal, this is what you have in terms of the Fermi surface of the material. This tells you basically where the electronic energy levels are as a function of momentum, which is the quantum number for electrons in crystalline solids. And you can take an alternative view here, which is you can cut through this reciprocal space by showing let's say these two momentum axes here and energy on the vertical axis, and then you see the electronic bands. Those are the electronic levels where the electrons lie as a function of momentum. And this situation here where you have a ferromagnet that has spins pointing up corresponds to a situation, an energetic situation in reciprocal space where the bands that have the spins, the electronic bands that have spins pointing up, have lower energy. Okay, and therefore you want to populate those bands with more electrons than the bands that have spin down. And that leads to sort of like a Fermi surface for the spin up, which is larger than the Fermi surface for spin down. The area of the Fermi surface is proportional to how many electrons you have. And so if you look at this, you can easily convince yourself that you have more spin up electrons than spin down. And so you have a total net spin up or total net up magnetic moment. A lot of interesting applications and phenomenology of ferromagnets, like way too many to be summarized in a slide, but I just want to flesh out a couple. Like the anomalous Hall effect is a very peculiar phenomenon that's displayed by ferromagnets. So this is sort of like a transverse current that arises when you apply a longitudinal current in the presence of a magnetization. So there's a transverse current or a transverse voltage that's created. And in materials that are also topological, so they have non-zero Chern number, this can lead to a non-dissipative transport through these so-called edge states. Another important application, which is this one is very relevant for especially data storage technology, is tunneling magnetoresistance. What you do is you interface two ferromagnets, and depending on whether they're both pointing up or they're pointing in different directions, up and down, you have an energetic alignment of the electronic bands, which tends to either favor or disfavor tunneling of these electrons across these magnets and across an insulating barrier. And so you can have that the tunneling barrier is reduced when you have a parallel alignment of these magnetic domains or magnetic materials, or it can be suppressed when you have anti-parallel alignment. Okay. Sorry, the tunneling barrier is increased. Sorry, so the tunneling itself is suppressed. And this is the mechanism that read heads in magnetic hard drives use to actually detect the local magnetic bits. Right? So that you have these read heads that run, or the disk runs under them, and then they detect whether there is a spin up or a spin down domain by measuring this tunneling currents. So another example of magnet is the antiferromagnet, and these were discovered much more recently, especially compared to the long history of ferromagnets. This is a discovery from the 19th century, especially the work of Neal. Antiferromagnet, the main difference is that now you have a staggered spatial organization of the spin. So you have alternating up and down in your lattice. And as a result of that, the unit cell, the magnetic unit cell of the material is enlarged because now you have two magnetic sublattices. So you have two inequivalent magnetic ions in the unit cell with opposite spins. And if you apply a time reversal operation now, same as we did for the ferromagnets, now what you do is you simply change the colors at each side. So you just invert the spins. And so you look at this picture now, and you're like, well, it kind of looks similar to what I had before, except that now everything is shifted by one lattice unit, right? So it's not quite exactly the same. But it turns out that you can apply another symmetry operation, another transformation, which is an inversion. And you want to choose carefully your inversion center. So I'm choosing here an inversion center, which is in the middle of the bond. And now what I'm doing here is I'm just switching these magnetic moments across this inversion center. And then I essentially recover exactly the same pattern I had in the beginning. So a magnet which behaves like this is known as a PT symmetric magnet. Okay? So it's compensated. You have an equal amount of spin up and spin down bands, and you have this underlying PT symmetry, which is very powerful because it leads to an effect or a property that's known as Cramer's degeneracy. So what that means is that the spin up and spin down bands are degenerate in reciprocal space, so they lie on top of each other. And when you look at the Fermi surface, if you have an antiferromagnetic metal, let's say, you have an equal amount of spin up and spin down electrons. So it's a very, very clear picture. By the way, I should have said that at the beginning of my talk. If you want to ask questions, please feel free to interrupt me. I prefer that much better than doing it all at the end, like when things are fresh. So just raise your hand and just feel free to interrupt me. Famously, when he gave his Nobel lecture on, for the Nobel Prize that he was awarded for the theoretical proposal of antiferromagnetism, which was later eventually discovered experimentally, was one of the very first success stories of neutron scattering. So Neal said that so these materials are interesting, but do not appear to have any practical applications. He was very skeptical. He was like, yeah, I mean, they're cool. But this compensation of the spins, the zero magnetization, that you can't really do anything useful. It was not entirely wrong, but there have been recent developments in the field of antiferromagnetic spintronics, for example, where there have been demonstrations of devices where you can actually read and write an antiferromagnet. So in ways that Neal could have never imagined back then, but then there's been almost like a whole century of developments. And there's phenomena such as the so-called Neal spin orbit torque, where if you apply a current in your material, the electrons that are part of this current, they can exchange angular momentum with your spins, but they can do so in a way which is different for the spins in one sublattice of your antiferromagnet versus the other sublattice. And so this is sort of like a staggered spin orbit torque, where there's this exchange of angular momentum. And so applying currents along specific directions, you can actually flip the direction along which the spins are pointing. So you can encode information in the direction along the direction that the spins are pointing. So this axis here, for instance, versus this horizontal axis here, right? And then you can also read that using a phenomenon known as the anisotropic magnetoresistance. I won't get into the details. This is just an example. But anyway, this is up until a few years ago, these were the main two classes of magnetic materials that were known. So ferromagnets and antiferromagnets, these are the main properties. So ferromagnets, magnetization, time reversal symmetry, and therefore also PT, so inversion and times time reversal is broken. There's a uniform real space spin density, which means there is a net magnetization. There's a K-space spin splitting, so the bands are split in energy up and down. But these are all reasons that make them good for applications. There are also some properties that make them less ideal for applications, like ferromagnets suffer from long-range dipolar stray fields, which tend to lead to demagnetization of magnetic domains when you make them too dense. Also, the switching speeds are fast, but not as fast as you can have in other kinds of magnets. So we're talking about gigahertz frequency range, so nanosecond switching. But they have, strong non-relativistic signals, like this tunneling magnetoresistance, for instance, is a very, very large effect. Antiferromagnets, there's no net magnetization, so it's perfectly compensated. PT symmetry is unbroken, or it is a symmetry in the system. The spin density is modulated spatially, no spin splitting in the band structure. And these are less than ideal properties, but then there are some properties that are actually better than the ferromagnets. Specifically, the antiferromagnets have no stray fields because there's no net magnetization, not even at the atomic scale. So there's no dipolar fields that can actually depolarize domains. And the spin dynamics in antiferromagnets are in the terahertz energy range, which means you can switch them even faster than like sub-nanoseconds, so even faster than ferromagnets. The big problem of antiferromagnets is that these effects, like these antiferromagnetic spintronic responses, are very, very weak. They're very, you can kind of see the magnitude here, right? It's like the change in resistance is like 0.1%. It's extremely small. Compare that to tunnel magnetoresistance, which is tens of thousands of percent. Like these are huge changes. And that's primarily because the effects that allow kind of spintronic responses in these materials are of a relativistic origin. So you can make your electrons as fast as you want, but that v velocity of the electron over c will always significantly suppress the magnitude of those responses. So now bring into the field this new class of materials, these altermagnets, which are kind of like a hybrid between ferromagnets and antiferromagnets. So operationally they have properties that are borrowed from both of them, but in terms of symmetries, they're actually distinct. And I'll make that case now when I introduce them. So to construct an altermagnet, like a simple kind of altermagnets, there are actually many different types that you can construct. But one of the simplest types is the one where you take an antiferromagnet, like the one we had a few slides ago. And then the only thing you do is that now you add a non-magnetic ion species, which is this white spheres, and you put them along the bonds, and you orient them in such a way that the local crystallographic environment around the spin-down sites, or the down magnetic sites, is different than the crystallographic environment around the up magnetic sites. So let me illustrate this. So the magenta site here, so spin-down, has this kind of diamond here, which is elongated in the horizontal direction, whereas for the blue site, is elongated along the vertical direction. Now, does this have the properties that an antiferromagnet, like the one we introduced before, has? So if you apply time reversal, you change the direction of the spin. So now magenta becomes cyan or blue or whatever, and vice versa. But the local crystallographic environment stays the same. The time reversal operation doesn't do anything to that. Okay, that's fine. What about if you apply an inversion operation on top of that? Would we recover this PT symmetry that like a simple antiferromagnet has? So you can try that around the same inversion center we had before. And the problem now is that the horizontal pointing diamonds become vertical pointing diamonds, and vice versa. What were before the vertical pointing diamonds become now horizontal pointing ones. Because now that inversion operation has changed the crystallographic environment around those magnetic ions. So PT symmetry is broken. So these are different than the antiferromagnets we introduced earlier, even though on the surface they look very similar, right? It's a square lattice of magnetic ions up, down, up, down. But it turns out that the local crystallographic environment makes a huge change for the symmetry properties. There's different symmetries, though, that can help us understand these materials better. For instance, suppose you apply a rotation now. So if first you do a time reversal, so let me go back. So first you have the time reversal version, and then you rotate it by 90 degrees. Now you can kind of compare these two, and you can sort of convince yourself that they're the same. Right? So now there's two lattices with the magnetic ions plus the non-magnetic ions in between them. They look exactly the same. So both the crystallographic environment and the location of the magnetic sites is unchanged. Which means that this transformation, which combines a time reversal with a rotation of 90 degrees, which this is kind of operation C for Z, it just means you rotate by 90 degrees along the Z-axis, is a symmetry of the system. So this is a rotation times time reversal, which is now a symmetry of this particular type of arrangement of ions. So this is the real space picture. What does this look like in reciprocal space for the bands, for the electronic bands? And the idea is the following. So suppose that you have only one band that has spin down, and it's this is the Fermi surface of that band, and it's elongated along some direction to reflect the crystallographic anisotropy around the spin down sites. Okay, so there is some anisotropy that's reflected in the shape of this Fermi surface. It's not circular anymore. This is for the spin down. How is this going to look for the spin up sites? Well, there is this operation that relates the two, right? It's a time reversal and the rotation. So you just simply apply time reversal. So you change magenta into cyan, and then you rotate it by 90 degrees, and you get this now sort of ellipsoid that's elongated along the kx direction, so in the horizontal direction. And so this is interesting now, because even though the area of these two Fermi surfaces is the same, which means you have the same amount of spin up electrons and spin down electrons, there are regions where actually the spin up electrons have lower energies, like here, because they have larger momenta, so they're pushed down in energy. And there are regions where the spin down electrons have lower energy. And you can see that in this kind of side view of the band structure, where you have momentum now on these two projections here and energy. And what you see is that when you go from kx to ky direction, there is a spin splitting between spin up and spin down band, but that changes sign as you change the direction in reciprocal space, so that overall, as a net, when you integrate across your whole Brillouin zone, the spin splitting is basically zero. So there's an equal amount of spin up and spin down electrons if you count them. But there is a net spin splitting, and it turns out that makes a huge world of a difference when it comes to spintronic responses. And importantly, and I'll get back to this later, this spin splitting here is not a relativistic effect. It's not a weak effect. This spin splitting is due to essentially the energy cost that it would take to flip one up spin here into becoming a down spin. And that energy cost is of order of the magnetic exchange interaction, which in magnetic materials can be as large as hundreds of milli-electron volts, or sometimes even a few electron volts. That's a very large energy scale. So these spin splittings are not weak effects. They're as big as you have in ferromagnets. Okay, so now these are sort of these three classes of magnets according to this new classification. So ferromagnets, altermagnets, and antiferromagnets. And you can see the reciprocal space picture that we've just discussed. And what's interesting is that sort of altermagnets get the best of both worlds in a way. So they get the stronger non-relativistic signals from ferromagnets, but they get the absence of stray fields from antiferromagnets because they're compensated. And then on top of that, you still have these large exchange interactions in the systems, which means that the spin dynamics are in the terahertz frequency range, so fast switching. This is all on paper, of course. This is still fantasy, right? So there's no device, there's no reality yet. But this is, on paper, what's supposed to happen, and that's one of the reasons why people are excited about exploring this new class of materials. Another interesting angle, when you look at the reciprocal space, is that if you plot the amount of spin splitting as a function of the angle in the Fermi surface, you see that for a simple ferromagnet, this is uniform. So the spin splitting is the same here, 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 here. It doesn't change, right? So it's uniform. So it kind of has the same like shape as an s orbital, which is a uniform orbital, or an s wave pairing function in a BCS superconductor, for instance. But altermagnets, they have this alternating spin splitting. It's negative here and positive here, negative here and positive here. So it changes sign. And they can have these kind of different form factors. Like this is a D wave, for instance, right? Because you have two nodal lines or two nodal planes, actually. And then you have this four-lobe structure, which is characteristic of D wave orbitals. And so this is the same spin splitting function as the gap function in the cuprates, in unconventional superconductors, for example. There's very interesting analogies, by the way, between altermagnets and superconductors, which I'm not really qualified to discuss because I'm not a theorist, so I'm just gonna leave it out of the picture. But there are some interesting aspects there. So these were predicted in 2020, so it's a relatively recent new field. And then since then, there have been a lot of predictions of a lot of materials to the point that some of the founders of this field, they like to go around and say that these were hiding in plain sight because there's a lot of altermagnets. We just didn't know that they had these properties up until this theoretical formalism was developed. This is an example. This is a simple rutile structure, which is the kind of cartoonish picture I provided earlier. This is ruthenium oxide, which was one of the first proposals. Actually, it turns out ruthenium oxide is not really magnetic in the bulk. It can be magnetic in thin films. That's still debated, but there are other candidates that have been now, shown to be altermagnets based on band structure studies. So this is angle result photoemission, the technique that John mentioned earlier, where you map the band structure as a function of energy and momentum, and you can see the spin splitting between the bands, and you can compare that to DFT, and you see that the spin splitting sort of changes sign when you change the direction in reciprocal space. Okay, so there were like quick follow-up experimental studies to test the predictions. You can actually predict the band structure of these materials using DFT quite accurately, and then you can compare that to experimental results. And now everyone is a believer that altermagnets are a real thing. And then people started thinking about applications. Okay, so what can we do with these altermagnets? And one idea is the so-called altermagnetic tunnel junction. So suppose you have two altermagnetic layers, and then you have an insulating barrier in the middle. So this is the equivalent of a ferromagnetic tunnel junction, except that instead of two ferromagnets, you have two altermagnets. And now this is the Fermi surface of the two altermagnets with the spin splitting being negative, positive, right? So suppose now you align these two spin splittings to be the same. So on the horizontal axis, it's always positive spin splitting. On the vertical axis is always negative spin splitting. That's a parallel configuration, which is very similar to the up parallel configuration in a ferromagnetic tunnel junction. But you can also have the opposite, right? You can have an anti-parallel configuration where now in one layer the spin splitting is positive in the horizontal direction, the kx axis, but in the other material is negative along that horizontal direction, right? And so now you get essentially that the probability of tunneling for electrons going through this barrier is essentially proportional to the overlap between the bands in these configurations. And it turns out that the parallel orientation has a transmission which is significantly higher than the anti-parallel orientation by something which is, at least according to calculations, well in excess of 100%, okay, which is sort of like the range where it becomes interesting technologically. Other possible spintronic applications, maybe I should actually get going a little bit more now, faster, to touch on the specific material I wanted to tell you about. But you can generate spin currents, which is a big challenge in spintronics is how to generate spin currents. With these materials, you can generate both longitudinal and transverse spin currents, but I'll skip that. And so now if we look at these two main classes of materials, these ferromagnets and these altermagnets, I'm leaving the conventional antiferromagnets out of the picture for now. There is this classification that's based on the symmetry of the spin splitting, right? S wave in one case versus D wave, or you can also have G wave or I wave, depending on the number of nodal planes or the number of sign changes in your spin splitting. But you can generalize this, right? So you can have a P wave, right? So that's an effective L equals 1, a gap function or a spin splitting function. And one thing that I want to point your attention to is that in a P wave, this has to have the same shape as a P wave orbital. What characterizes a P wave orbital is that it's odd parity. So if you go from one lobe to the other, the sign of the wave function for a P orbital for, let's say, an electron in the hydrogen atom, changes sign, right? So you go from positive to negative. And that's the same sign change you have in the spin splitting between the electronic bands in a P-wave magnet. You go from positive in the positive x direction to negative in the negative x direction. But there's an important implication of this, which is that if you apply an inversion operation, so if you flip right to left and left to right, then you actually end up with a reversal of that spin polarization, right? So a requirement for P-wave magnetism is that your magnetic system has to break inversion symmetry. And so a natural candidate class of materials where to look for something like that is non-collinear magnets, because non-collinear magnets have many ways that they can break inversion symmetry. I'll illustrate a few with the example of a specific material today. In non-collinear magnets, generally, they are centrosymmetric, at least when it comes to the spin degrees of freedom. The ions can break inversion symmetry, but that's a trivial way of breaking inversion symmetry. Right, so there's interesting applications for P-wave magnets as well. You can construct the same type of magnetic tunnel junction, but now you can put these P-wave lobes pointing in the same direction or pointing in opposite directions, and this will give you a contrast in a tunneling measurement. So this is another way of doing a tunnel junction, very similar to the D-wave altermagnets. So what are the good materials candidates for P-wave magnetism? So we said we want something which has a spin-induced inversion symmetry breaking. So, a good place to look for these things is non-collinear magnets. And then we want some kind of two-fold symmetry, right? Because the P-wave orbitals have this sort of two-fold symmetry where you kind of rotate them by 180 degrees, then you get back to some kind of you restore some kind of symmetry. They have this kind of two-fold nature to them. And so spin spiral magnets is where we've been looking for this very exotic form of magnetism known as P-wave magnetism. So this is an illustration of a spin helix. It's a freestanding spin helix. So it's just spins floating in space without a lattice. So these are spins that are not sitting on, they're sitting on a chain, but they don't have a crystallographic environment, right? This is a freestanding chain. And it has a handedness to it. So the helix is this is a proper screw spin helix, which means that the spins rotate in a plane that's perpendicular to the axis of propagation, right? And now suppose that you have a conduction electron that's moving across the spin helix, right? So now there is a charged particle that's moving across the spin helix. So let's look at what happens from the perspective of that particle. So you have your conduction electron is going down these chains of spins, which are kind of rotating, right, as the electron propagates through. So if we look at things from the frame of reference of the electrons, what you're seeing is really you're seeing a magnetization that rotates around like this. And that's something familiar, right? Because that's what happens when you take a magnetic moment and you apply a magnetic field perpendicular to it, and that will induce a Larmor precession, right? So this phenomenon, you can think of it as essentially like an inverse Larmor precession kind of thing. And what that tells you is that from the perspective of the electron moving into, from the perspective of the electron in its frame of reference that sees this kind of rotating spins, there has to be like an effective magnetic field that causes that precession, right? And that magnetic field has to be pointing in the same direction as the propagation of the electron, which means it has to be pointing in the same direction as the helix itself. And that's an emergent form of magnetic field. It's actually a Barry phase effect, which can be shown theoretically how it arises. If the electron moves in the opposite direction, then the spins will wind around in the opposite direction. And so the effective magnetic field that this produces is pointing in the opposite direction, right? So this is like a fundamental notion of helicity, which is like a relationship between sort of the spin of a particle and its velocity. So what you see here is that as the electron moves in one direction versus the other, there is a different effective field that acts on the spin of that electron. And what it will do, interestingly, is that if the electron moves to the right, that magnetic field will be pointing in one direction and will be trying to promote a certain arrangement of that spin of those electrons in that direction. Whereas if the electron is traveling to the left, then this is again a reciprocal space picture, then the magnetic field will promote the opposite spin orientation. And that's exactly the symmetry you have in a P-wave magnet. So that's why spin helices or spin spirals more in general, they're a good platform to look for these things. You reverse the chirality, and then sort of the direction of the precession reverses, and so all the magnetic fields, they reverse. So this is not a great slide, actually, because you can't see a lot what's happening here. But some people like to refer to this as to the kinetic magnetic effect. It's an emergent momentum-dependent magnetic field. It's not a real magnetic field. There's no actual magnetic field you're applying. But from the perspective of the electron that's moving in this background of precessing spins, it feels very much as if there was a magnetic field. So it's the same form as a Berry connection is for topological materials, if you like. And what it does is you take this band structure, you have these parabolic bands, let's say, and it splits them in momentum. It splits them sideways such that spins pointing in one direction are favored energetically on one side for positive momentum, but for negative momentum, you favor the other spins. And that's the P-wave kind of symmetry. There is a model, that simple model of electrons propagating in helices that actually is exactly solvable in a particular limit. And there's a unitary transformation in that model that shows that basically, how these kind of momentum-dependent spin splitting arises. But this goes beyond. I don't have enough time to discuss this. I'm actually already quite late. So let me tell you about the material that we've been studying. So this is nickel iodide. So it's a very simple stoichiometry. It's just nickel iodine shoe. It's also a relatively simple unit cell with just three layers, and the nickel ions are the magnetic ions. So those are the ions that are carrying the spins of the magnetic moments, and they occupy the sides of a triangular lattice. Okay, so the nickel forms a triangular lattice, and then the iodines are just decorating around the nickel planes, and they're coordinating to it. So at high temperature, this is a fairly high symmetry. So it's a rhombohedral symmetry. So you can see the light blue spheres are the nickel ions. You can see that they occupy the sides of a triangular lattice. And at high temperature, there's 3 two-fold axes, there's 3 mirror planes, and there is inversion symmetry. So there's a very, very high symmetry in this system. Interestingly, what happens if you look at the exchange interactions between the spins, and if you look at spin-spin exchange interaction nearest neighbor, next nearest neighbor, and next nearest neighbor, so like second nearest neighbor and third nearest neighbor. So the second nearest neighbor ends up being negligible. This is from the density functional theory, by the way. But the first nearest neighbor and the third nearest neighbor, they have almost the opposite, well, they have almost the same magnitude, but the opposite sign. And for those of you who were at the discussion earlier, if you remember, that is the exact condition that you want to have to realize some kind of non-collinear state, right? Because now you have a competition between an interaction, which is negative J, so it tends to favor ferromagnetic alignment of the spins, and an interaction which has positive J and almost the same magnitude, which tends to favor anti-parallel alignment of the spins. So the material doesn't know what to do. Is it going to go parallel? Is it going to go anti-parallel? Can't decide. So it does something in between, which is it develops this kind of helical pattern. So it's this longer pitch helix where the spins are not quite parallel, they're not quite anti-parallel, they have an angle in between them, and that as you change that angle, as you go along the helix, then you go from a spin up and then back eventually again to spin up, right? So it's still a periodic system, but now the magnetic cell is very big because you have this helical pattern, and you can have a helix that has kind of both left or right chirality, right? You have a choice. So the spins can rotate like clockwise or counterclockwise. There's another important detail, which is that the spin rotation plane is kind of a little bit tilted, so the helix is not propagating in a direction in the triangular planes, but it's actually going out as a projection, which is along the c-axis, but that's in a way kind of like a small detail, which is not super important for the physics of the material. This helix has a wave vector of 0.14, which is roughly 7 unit cells in real space. And the signatures of this transition to this highly magnetic state with the spin helix are very clear already in the magnetization measurements, where you see this kind of drop of the magnetization at about 60 Kelvin temperature. And what happens concurrently with that magnetic transition is that you develop a charge polarization. You develop actual electric dipoles in the material. There is a ferroelectric, there's an improper ferroelectricity in the material. So what happens is that there are electronic dipoles that form, and these electronic dipoles form because the spins break inversion symmetry. And there is an underlying interaction that when that inversion symmetry is broken, allows for these electronic dipoles to form. So the dipoles are pointing in this direction, the vertical direction, up and down. As you reverse the chirality, which you can do by applying an inversion operation, you automatically also reverse the dipoles. They transform identically under the same operations. And you can measure these dipoles by measuring the depolarization current, which is a form of displacement current, essentially. You cool down your material very rapidly, and as this electrical polarization develops, you have a time-dependent polarization or a time-dependent electric field inside the material that produces a current. And that current can be integrated, and it will give you a charge, and that charge is the polarization. So, and you can see very clearly that the moment you enter this magnetic phase at low temperature, you have this sudden change, sudden bump, and a transition to a ferroelectric state. So the spiral magnetization is actually modulated, so the components of the spins are modulated spatially, and so it is similar is the case for the electrical polarization, but there is a total net polarization, so the material is actually a ferroelectric. Now we can see the helices with magnetic Bragg diffraction, so these are the signatures in reciprocal space of the helices. I will not talk about this because it's not super important for the talk itself. And so you can detect the helix experimentally, and then you can measure the ferroelectricity at the same time. You can do a measurement like the one I discussed earlier, or if you work with thin materials, because this material is also van der Waals material, so it's a 2D magnetic insulating material, which can be exfoliated like graphene. It can be reduced to all the way to monolayer, if you like. If you do experiments on thin flakes, then you cannot measure these very, very small currents, depolarization currents. So what you do instead is you do like a fancy version of the photovoltaic effect. So you turn your little material, little flake, into a solar cell, essentially. And what happens in a solar cell is that you have light that excites electrons, and then you want to collect a current out of that process, right? So you want the electrons to go in one direction and the holes to go in the other direction. And that only happens if there is an internal field in your p-n junction that pushes the electrons one way and the holes the other way, right? Now, there is no p-n junction here. That's an engineered form of inversion symmetry breaking, right? That picks a direction for the current. But there is an internal electrical dipole. And that dipole is effectively a built-in electric field that tends to push the charges one way or the other, right? So there is a photovoltaic effect in these systems that break inversion symmetry, and you can detect that essentially by just shining lights onto this junction here between these two electrodes and just collecting the current at zero bias. No need for external voltage. The built-in electric field of the material will provide that force that drives the electrons one way and the holes the other way. You can see here that photocurrent. If you field cool with positive field, then you have a net positive electric dipole, and so you have a positive photocurrent. If you field cool with the opposite electric field, then you have a net negative electric dipole, and so you have a net negative photocurrent. You can see the transition here is at about 60 Kelvin. It's actually slightly less because this is a thin flake, so the transition is slightly pushed down in temperature. You can do these measurements as a function of electric field. You can reconstruct the full profile of the polarization versus the field. You can see the switching, so you can go one direction and then it stays in the same state, and then it suddenly switches to the other state. This is the well understood ferroelectric hysteresis loop that all these ferroelectric materials display. And then there's the question of like, okay, well, what about the P-wave spin splitting? Because now I have to tell you the end of the story, right? So where are we going with this physics? So this material with the spin spiral has this kind of twofold rotational symmetry along this direction, which is the x direction. Okay, so as you rotate the spiral like this, sort of along a vertical axis, then the spiral will stay the same. So that's actually the only symmetry that exists in the magnetic state. It's a very, very low symmetry magnetic space group. When you apply like an inversion operation or a mirror, you flip the direction of the electrical dipole, you flip the chirality of the helix, and you also expect to flip the pattern of spin splitting you have in your P-wave magnet. So now it's orange on the right and blue on the left, and you switch to blue on the right and orange on the left, meaning that you favor one spin orientation on the right here and the opposite one on the left, and vice versa down here. I guess that's the bell that's telling me I should wrap things up. Okay, so if you do a band structure calculation, this is DFT with some ways of including electronic interactions. What's shown here is the spin projection. This is in the direction of the helix, and this is a positive spin. So red is positive spin or spin up. Well, let's say spin along the direction of the helix, and blue is spin in the opposite direction. And the horizontal axis here is the axis of the polarization. The vertical axis is the axis of the helix. So what you're seeing here is that along the vertical axis, which is the axis of the helix, as you go from positive momentum to negative momentum, the spin projection flips sign, right? You go from blue to red, red to blue. So as you just mirror on the other side, you go blue to red again. There is this inversion of the colors, which is not there in the other direction. So in the other direction, if you look, you got blue to blue, red to red. So this has already, you can see sort of the signatures of this P-wave kind of symmetry. If you invert the chirality, the colors switch as expected by symmetry. So now red becomes blue. I'll play it again quickly. Red becomes blue and blue becomes red. Very clean. So this is kind of this. So this has the right symmetry for this kind of P-wave or odd-parity spin polarization, where you favor one spin along for positive momentum and the opposite spin for negative momentum. So how do we probe this experimentally? And there's another optoelectronic measurement which can be done, which is kind of similar to the bulk photovoltaic effect, but it's a little bit more sophisticated. And in practice, it's essentially the same measurement as the bulk photovoltaic effect. You shine light into your material, you collect a photocurrent, except that now you shine light that has positive helicity, so let's say right circularly polarized light, and then you shine light that has negative helicity, so left circularly polarized light. Okay, so you use these two helicities, and then you look at the difference in the photocurrent. And you might wonder, well, how does that help us? Why does that matter? Well, suppose you have this simple cartoon of the band structure, right, where you have, that you have spin down on one side, spin up on the other side, and maybe this is reversed in the conduction band, and this is for one chirality, and this is for the opposite chirality, right, where all the colors change across this horizontal axis, right? So now, if photons carry angular momentum, you can have a transition where that angular momentum can be exchanged and can be passed on to the spin, right, through spin-orbit coupling. So, for instance, right circularly polarized light can excite an electron from a spin-down band to a spin-up band, and vice versa. Left circularly polarized light can excite an electron from a spin-up band to a spin-down band. In other words, you change the angular momentum, you transfer angular momentum from the photons to the electrons, to the electronic spin. And so this is interesting because what that means is that one circular polarization will try to excite electrons primarily on one side. The other circular polarization will try to excite electrons primarily on the other side. And so you expect two photocurrents, one which is positive, one which is negative. And so if you take the difference, you expect a signal which is finite, right? And the sanity check is that that signal is supposed to change sign for the opposite chirality. And so we did this experiment. So this is the device. So you have two terminals, one that collects the current along the direction of the helix, which is where you expect this contrast between left and right circularly polarized light. And the other pair of electrodes is in the perpendicular direction where you do not expect that contrast, because that's the direction that's perpendicular to the lobes of the P-wave, where there's no sign change, right? And so what we see is that when we collect this photocurrent with right circularly polarized light versus left, there is a very, very clear difference in the total amount of photocurrent that we get. And you can calculate the difference, and you see that it has this sign change as you change the polarization of light. You go from linear to circular, back to linear, back to circular, back to linear. As you can see, the linear is always the same, but the circular ones are actually changing. They have quite a significant contrast. If you change the chirality, you obtain this exact reversal of the photocurrent, the difference in the photocurrent, left to right circularly polarized light. This is called it was in the previous slide, this is called the circular photogalvanic effect. So reversing the chirality, which we can do by applying an electric field, because the chirality is rigidly coupled to the polarization, reverses the circular photogalvanic effect, which is already a direct signature of this P-wave spin polarization. if we now do the sanity check, well, actually, before that, one sanity check is the temperature dependence, right? So if this effect is really due to the spin spiral arrangement in the material, it should go away as you warm up above the helimagnetic transition temperature. And that's pretty much what you see. And this effect is there if you switch from left to right, you have this kind of square wave where you go from high to low photocurrent. And then this becomes flat at 60 Kelvin, which is above the magnetic transition. And same for the opposite chirality. So this already tells you that this is an effect that only manifests itself in the magnetic phase. And the other important sanity check is to look at the perpendicular direction, where you do not expect to have this sign change in the spin splitting, and you do not expect to have any circular photogalvanic effect. And indeed, what's shown in the measurements is that if you compare left to right circular polarization, they end up being the same. So there's no contrast between them, which is, again, compatible with this twofold spin splitting pattern. Now, my very last slide before, actually, this is my very last slide, yes. So we've been trying to build devices, the same device that I illustrated in the beginning, right, where we have this orientation of the spiral, which is either parallel or anti-parallel, right? So you can see now there's two layers of nickel iodide separated by a barrier. And then in one layer, we have, in one configuration, we have that the chirality of the spin spiral is the same. Sorry, actually, that's one at the top. Sorry, the chirality here is the same. So the handedness of the helix is the same. Or it's reversed over here, right? In order to be able to reverse it, you need to have a way to control the chirality of one layer with respect to the other, which actually turns out it's a big challenge. If you want to know more, you can feel free to stop by and I can tell you more about it. But importantly, what we found in these measurements, oops, that's too fast, is that there is actually a contrast for a fairly large bias, because this is it's a lot of insulating material, so you have to go to quite high voltages, but there is a contrast of about 35%. The amount varies. In some devices, we've seen 10 to 15%. In other devices, we've seen 30 to 35%. We've seen this now in multiple devices where we have essentially same chirality or parallel chirality versus anti-parallel chirality, and we see this chiral contrast in the magnetotunneling through these devices. And this is, again, this reflects essentially the physics of these P-wave magnets, and one possible way to sort of harness that physics in some kind of device application, right? Now, this is not very useful because it only works at 30 Kelvin. No one wants to cool down their hard drives to that temperature, but this at least it's a proof of principle, which is important eventually to kind of start exploring these things in materials that have more promise for applications. But the physics is very fun, and I think that this shows that these things are real and they have a real impact in these kinds of devices. And that's all I have. Thanks again for having me. I'll be happy to take questions.
So we have a few minutes for some questions. Great talk, by the way.
Thank you.
Yes.
What do you say is the difference in P-wave?
Yeah, so I can repeat the question, John. If you want to say it again.
Okay, I'll repeat it in the mic then. What would you say would be the difference in applicability between P-wave and D-wave altermagnets?
I don't think there's, I mean, in terms of symmetry and mechanism, no, I think it's the same. Like it's a matter of testing these in different materials and seeing, looking for the ones that will produce a large tunneling magnetoresistance, right? So nickel iodide is pretty modest because it's only like a few tenths %, right? So it's fairly small compared to ferromagnetic tunnel junction, which is 1,000%, or something like that. I don't know of any demonstration of D-wave tunneling junction, although I know people are working on it, so there's no term of comparison. But in terms of this, there's no reason why one should be working better than the other. The mechanism is very similar. You have these spin splittings, and you want to kind of put them have them work against each other for the low tunneling current state, and work together with each other for the high tunneling or on state versus the off state.
Other questions? Maybe I can ask you one. So I guess this loosely falls under the rubric of a multiferroic effect, right? Even
Yeah.
though it's a lot more exotic.
Yeah.
Can you do the opposite? Can you apply magnetic field and induce a current in this case?
That's a very good question. Yeah, so the material is a multiferroic, and we've been studying it for many years because we were interested in the multiferroic properties. So there's also coupling between the spin and the charge. So you can control the magnetic ground state with electric fields. The reverse effect, which you're suggesting, so to use magnetic fields. So we've explored that a little bit for some reasons which we do not yet completely understand. The material is remarkably impervious to magnetic fields. It just doesn't care. Up to 14 Tesla, just doesn't care. The helix is pretty much unchanged. Properties are pretty much unchanged. That's very different from a lot of other frustrated metallic magnets where you have non-collinear phases or even some non-coplanar phases like skyrmions. And then when you apply a magnetic field, things change a lot, even with very, very modest magnetic fields. Those are much more susceptible. I think here, because of the nature of the exchange interactions, this helix is remarkably stable to magnetic field. So, yeah. What you can do with magnetic fields together with electric fields is to control the chirality. That goes under the name of magnetoelectric cooling, and that's a way to control the chirality of the system.
Maybe just a simple question. So in your cartoon, you had this nice helical chain. In the actual compound, can you just like sketch out where is the sort of analogy to the chain?
Yeah. So the helix is sort of imagine it going a little bit out of the, so it has an in-plane component which is along this horizontal axis, and you can kind of see that the rotation of the spins, right? There is an in-plane component, but there's also an out-of-plane component because the spin rotation plane is actually tilted like this. So the helix axis is perpendicular to it, so it comes out of the page and has an in-plane component but also an out-of-plane component, which is not that doesn't change anything as far as the P-wave physics, but it's there. Yeah,
in the symmetry of the crystal itself, let's say at high temperature, is there anything that selects like a direction for this winding at all, or no?
Great question. No. So there's 3 domains. So there's 3 equivalent Q domains that are the principal directions of the triangular lattice. So this is one, this is another one, and this is the third one. So you can end up with all 3 domains. The one way that we can make a monodomain state in thin flakes is by doing a field cooling. So we cool in an electric field, and then the material is forced to choose one specific direction, which has a polarization which aligns to the electric field. And that's how we can essentially cool down the material into a single domain state. But if we don't do that, then you will see all 3 domains. So there's like a domain structure in the material.
Just a quick question, I guess. Have you looked into any other materials other than nickel iodine, I guess? Iodide?
Yes, we have been looking at nickel bromide, although it's a bit harder to study because with this sort of optoelectronic probes, because it's a larger band gap, so you have to go to like almost near ultraviolet kind of excitation, which is challenging. And yeah, not a lot more others, honestly. I mean, we really like nickel iodide, and it exfoliates well. We know the material very well by now. We've studied the properties also from the theoretical standpoint for several years. So we're starting to explore other systems with similar physics, but for the most part, we've been looking at this specific material. There are other candidates, though, that have been proposed not by us, by other groups that are spin spiral and are also supposed to show this P-wave magnetism.
So I was wondering, it seems you may, for application purposes, want like a metallic altermagnet.
Yes.
But then for this case, since it seems to be fairly insulating, would it make sense to try to tunnel through it rather than to measure directly with, say, photocurrent or something? So I don't know, maybe you have 2 layers of this thing and you try to switch the chirality of one with respect to the other, and you could form like a magneto-tunnel junction type device that way.
Yeah, great question. Like, why the tunneling barrier in the first place if we have two insulators, right? So that's a great point. In principle, you don't need it. Yeah, I'm not sure how the modeling would go for just two nickel iodide layers on top of each other, but I suppose that's possible. The reason why we have the insulating barrier in the middle, which is HBN, is actually not so much to have a barrier, but it's more so because it creates a separation between these layers, which allows us to switch them independently. And that gets into the specifics of how to switch the chirality of one while keeping the chirality of the other unchanged. Right? That's a big challenge, right? In in ferromagnetic tunnel junctions, you do this by using a pinning layer, right? So you have fixed layer, free layer, and then the pinning layer pins the fixed layer, right? So you don't have to worry about switching that with a magnetic field. So we don't have that luxury here, or at least we don't know of any material that could provide pinning of a certain chirality, and so we have to instead try to control the two layers independently. And hexagonal boron nitride, it turns out it helps out with that, and I can tell you the details a bit later if you want. Yeah.
Okay, I guess we're out of time. So there's so many interesting questions. We'll just have to invite him back for a seminar or something like that next time. So let's thank Ricardo.
Always happy
again
to
for
escape the
great talk.
US these days.
Yes, that's right. Not very far away. Okay,
Right.
thank you very much for coming.